A modern container ship can stretch nearly 1,300 feet in length, rise more than 230 feet above the water, and carry over 20,000 steel containers, making it look like a colossal city silently drifting across the ocean. Beneath those towering stacks lies a steel structure weighing hundreds of thousands of tons, an engine as large as a building, and a network of systems powerful enough to withstand massive waves, violent winds, and voyages spanning thousands of miles. What makes this engineering marvel even more remarkable is that the entire giant is assembled from flat steel plates, individual welds, and countless components that must fit together with near-perfect precision. So how do humans transform raw steel into one of the largest transportation machines on the planet? Join Factron process as we step inside the shipyard and uncover the extraordinary journey behind the construction of this ocean-crossing giant. Across the world's oceans, container ships carry nearly every type of cargo that powers modern life, linking factories, ports, and markets into a vast global network. In 2025 alone, around 280 million containers were moved worldwide, equivalent to more than 760,000 every day. The total value of goods transported by this industry exceeds $4 trillion annually, accounting for roughly 60% of the value of global seaborne trade. That is why each megaship is more than just a means of transportation. It is a colossal floating warehouse crossing the ocean. When one of these vessels runs aground, suffers an accident, or becomes trapped along a critical trade route, the consequences can spread from ports to factories and markets across entire continents. The Ever Given incident showed just how vulnerable this system can be. A single ship blocking the Suez Canal was enough to delay nearly $10 billion worth of goods every day. The journey of building a container ship begins with thousands of marine-grade steel plates, each produced in different strengths and thicknesses. To understand the scale, the 1,296-foot-long NSC Oscar alone required approximately 45,300 tons of steel, a vast volume of material that must be tracked and managed plate by plate. Before fabrication begins, workers inspect the material certificates, thickness, flatness, and traceability codes to ensure that every plate is assigned to the exact location specified in the design. The ship's three-dimensional model is then divided into thousands of individual components and arranged across the steel surface using nesting software. This helps maximize material usage and minimize scrap. CNC machines guide plasma or oxy-fuel cutting heads to produce hull plates, frames, bulkheads, technical openings, and beveled edges prepared for welding. With a typical 130-amp plasma system, steel measuring 0.24 inches thick can be cut at approximately 13 feet per minute. When the thickness increases to 0.79 inches, the cutting speed drops to around 4 feet per minute. After cutting, each component is marked with an identification code, cleared of slag, and checked for dimensional accuracy before being transferred to the forming stage. After cutting, the plates intended for the bow, stern, and curved sections of the hull are passed through rolling machines or hydraulic presses. The steel is bent gradually and continuously compared with the design data until the required curvature is achieved, after which it moves on to assembly. Welding begins by placing the steel plates on a flat panel line, aligning their edges, and temporarily securing them in position. Smaller plates are joined into large panels and frames. Longitudinal girders and stiffeners are then installed at their marked locations. Long, straight welds are commonly automated to maintain consistent speed and quality, while confined corners, curved surfaces, and complex structural intersections still require flexible equipment or direct work by skilled welders. The strength of each joint is not the only critical factor. The welding sequence is equally important. Heat causes steel to expand and then contract, so welds must be arranged symmetrically and completed in a carefully calculated order to reduce distortion. Shipyards may even include dimensional allowances in advance, anticipating how much the structure will shrink as it cools. After each stage, the panel is measured again for flatness and dimensional accuracy. Critical load-bearing welds are also examined using non-destructive testing methods to detect defects hidden beneath the surface. Once the steel panels are complete, frames, girders, bulkheads, and stiffeners are carefully aligned and welded together to form individual blocks, each representing a section of the ship's bottom, side shell, deck, or internal compartment. Every component carries its own identification code and coordinates to ensure precise alignment with the digital design. Before each block is enclosed, workers pre-install piping, cable trays, ventilation ducts, and equipment foundations. Many blocks are also turned upside down, so that welding and installation can be performed more easily, reducing the amount of work required in confined spaces after the hull has been assembled. Finally, each block is inspected for dimensional accuracy, flatness, connection point alignment, and weld quality. Only blocks that meet the required standards are approved for assembly into larger grand blocks or transported directly to the building dock. At the building dock, the completed blocks are transported into position in the exact order required for assembly and lifted by heavy-duty cranes. Construction usually begins when the first bottom block is lowered onto the ship's centerline, marking the keel-laying milestone. From there, additional bottom, sideshell, bulkhead, and deck blocks are installed one by one, gradually extending the hull in both length and height. Before permanent joining begins, every block must be precisely aligned, using laser measurement equipment and reference points built into the structure. Engineers check elevation, inclination, centerline position, and the gap between adjoining sections. This stage is especially critical because deviations as only a few millimeters at individual joints can accumulate into a significant misalignment across a hull nearly 1,300 feet long. It is temporarily secured and then welded to the surrounding sections, creating one continuous structure. At the same time, the prefabricated piping, cable trays, ventilation ducts, and equipment installed inside each block are connected across the joints. After every major joint is completed, engineers continue checking the centerline, structural deformation, and weld quality to ensure that any deviation does not carry over into the sections that follow. When the final block is lifted into position, the ship's basic form finally becomes visible. Yet inside the hull, countless systems, machines, and pieces of equipment still need to be installed before the vessel can leave the building dock. On container ships powered by liquefied natural gas, the LNG storage tank is one of the vessel's most critical systems. This tank assembly can hold tens of thousands of cubic meters of fuel and must keep the natural gas in a liquid state at extremely low temperatures throughout the voyage. To prevent heat from the surrounding environment from entering the tank, its outer surface is covered with multiple layers of specialized insulation. Polyurethane panels are tightly fitted and securely fixed in place, creating a continuous thermal barrier. Each joint is then tested using a vacuum method combined with a soap solution, allowing technicians to detect even the smallest leaks. Only after the entire tank has been confirmed completely airtight can the system proceed to the next stage of installation. The main engine is one of the largest and heaviest pieces of equipment aboard a container ship. It can stand as tall as a multi-story building and weighs several thousand tons. Before being transported to the shipyard, the engine is typically pre-assembled and tested at the manufacturing facility, then dismantled into multiple modules to simplify transportation. The crankshaft is one of the heaviest and most precision-critical components of the main engine. Before installation, the engine bed plate and main bearings are cleaned, lubricated, and checked for correct positioning. The crane slowly moves the crankshaft through the still open deck and lowers it onto the bearing supports, while workers use guide ropes to prevent unwanted rotation or impact. Once the shaft is in position, engineers measure its deflection, bearing clearances, and contact pattern along its entire length. Even a slight deviation can distribute the load unevenly, generate vibration, and accelerate bearing wear. Finally, the bearing caps are installed and tightened in the specified sequence. The crankshaft is then turned slowly to confirm smooth and stable movement before the connecting rods, pistons, and remaining engine components are assembled. Once the crankshaft has been positioned accurately on its bearings, the engine frame, connecting rods, pistons, and cylinder assemblies are installed one by one in the correct sequence. Heavy components are lifted by cranes, while every contact surface, clearance, and connection point is measured and inspected before being secured. Next, the cylinder heads, fuel injection system, lubricating oil lines, cooling water pipes, turbocharger, and exhaust system. The piping must be aligned naturally to avoid placing additional stress on the engine structure as temperatures change during operation. After the entire mechanical assembly is complete, engineers check for leaks, verify oil pressure, test cooling water circulation, and inspect the operation of the control system. The crankshaft is slowly rotated through several complete revolutions to confirm that the pistons, connecting rods, and bearings move in synchronization without contact or abnormal resistance. After factory testing, the engine is dismantled, transported to the shipyard, and reassembled in the engine room before being aligned and connected to the propeller shaft. While the main engine is being completed, the shaft line and propeller are installed at the stern. The propeller shaft is inserted through the stern tube, supported by bearings and precisely aligned with the engine's centerline. Even a slight deviation can cause vibration and rapid bearing wear during operation. The propeller, spanning dozens of feet and weighing tens of tons, is lifted by crane, carefully balanced, and positioned onto the tapered shaft end. Engineers apply a marking compound to the contact surfaces to verify a proper fit. Once alignment is confirmed, high-pressure oil is injected between the mating surfaces, allowing the propeller to slide firmly onto the shaft. The locking nut and protective cap are then installed, completing the ship's propeller assembly. After the propeller is installed, the remaining joints around the stern and hull are welded, cleaned, and inspected to create a continuous structure. Any areas affected during assembly are also repaired before painting begins. The hull is then coated with several layers of specialized paint. Anti-corrosion coatings protect the steel from seawater, while anti-fouling paint below the waterline reduces marine growth and drag. And recessed areas are carefully inspected to ensure the entire surface is evenly protected. From this point, the vessel officially enters service and joins the global maritime transport network. On each voyage, it can carry tens of thousands of containers, moving enormous volumes of cargo from manufacturing centers to markets thousands of miles away. It travels continuously between major ports in Asia, Europe, and North America, crossing critical trade routes such as the Strait of Malacca, the Suez Canal, and the Panama Canal. Each container is assigned a carefully calculated position to distribute weight and keep the ship stable in heavy seas. After arriving in port, the cargo is quickly transferred to trains, trucks, or inland vessels to continue its journey. Once little more than a mass of steel inside a shipyard dock, the vessel has now become a vital link that keeps global trade moving. From the first flat steel plates, thousands of components have been cut, bent, welded, and assembled into a massive container ship capable of crossing the ocean for weeks at a time. Its engine, shaft line, propeller, and countless onboard systems must work in precise coordination to carry tens of thousands of containers along the world's busiest trade routes. Yet, no matter how powerful it may be, no ship can remain in service forever. So what happens when this machine, weighing hundreds of thousands of tons, reaches the end of its working life? Is it abandoned as a worthless mass of steel, or are its components dismantled, sorted, and reborn as new materials? Keep watching, because the next journey will take us inside the enormous world of ship recycling.
Behind the stereotypes of poverty, India is actually home to the world's largest steel mine, where more than 100 gigantic ships are retired each year and reborn as millions of tons of steel that support global industry. From the moment a ship reaches shore, it begins to lose its original form. Valuable components are removed one by one, while the enormous steel hull is cut into pieces, swallowed by blazing furnaces, and reborn as new steel, ready to become the foundation of factories, bridges, and even the ships of the next generation. Join Factron process as we travel to India, where gigantic ships end their journeys across the oceans and begin an entirely new life cycle. For more than a century, ship recycling has become an important link in the global steel industry. Today, the center of this industry lies in Alang, India, the world's largest ship recycling yard, established in the early 1980s. In just over 4 decades, more than 8,900 ships have been dismantled there, recovering over 71 million tons of steel and making India the world's leading country in ship recycling. Remarkably, more than 95% of a ship's weight can be recovered and reused, from tens of thousands of tons of steel, engines and propellers, to kilometers of electrical cables. However, to transform a giant that once conquered the oceans into raw material for countless factories and new construction projects, each ship must undergo a process lasting more than 2 months, during which almost no valuable component is wasted. After more than 25 years at sea, the ship's voyage comes to an end at a dismantling yard. When fuel, maintenance, and repair costs exceed its operational value, many ship owners sell the vessel to recycling facilities, beginning a new life cycle for the tens of thousands of tons of steel and equipment inside. In India, many ships are driven directly onto the beach at high tide, using the force of the water to move steel structures weighing more than 50,000 tons into the correct dismantling position. Meanwhile, in Turkey, Europe, and the United States, ships are usually towed to a quay or floating dock, allowing cranes and heavy equipment to access them more easily. Immediately after reaching shore, the ship is secured with high-strength steel cables, anchors, and winch systems to prevent any movement caused by waves or tides. Only after the structure has been stabilized does the workforce begin surveying the entire vessel. They compare the original design documents with the ship's actual condition, identify the hull structure, fuel tank locations, estimated steel weight, and valuable equipment in order to create a detailed dismantling plan. Every cutting position is calculated in advance, because even a small mistake could destabilize thousands of tons of steel and endanger the entire dismantling operation. Although the ship is no longer operating, fuel, oil, bilge water, compressed gases, and various chemicals still remain inside and could cause fire, explosions, or pollution when hot cutting begins. The technical team pumps residual liquids from the storage tanks while removing batteries, gas cylinders, fire extinguishers, refrigerants, and equipment containing chemicals. Oil residue, contaminated water, and hazardous waste are collected separately and transferred to treatment facilities. On older ships, insulation and fireproofing materials may contain asbestos. These areas must be isolated, dust must be controlled, and the materials must be removed under specialized procedures. Finally, every enclosed compartment is ventilated and inspected using gas detectors. Only areas that meet safety requirements are authorized for hot cutting work. Once the ship has been confirmed safe, the dismantling team begins recovering equipment that can still be used before cutting into the steel hull. Inside the engine room, the main engine, generators, pumps, valves, and auxiliary systems are disconnected from electrical lines, pipelines, and mounting foundations. Smaller equipment can be lifted as complete units, while large engines usually have to be dismantled into multiple modules before being removed. At the stern, the shaft and propeller are also recovered separately because they contain valuable metals. After inspection, operating equipment is refurbished and resold, while damaged units are dismantled for spare parts or sorted by material for recycling. Once the valuable assets have been removed, the ship is gradually reduced to its main steel structure. Once the maze inside the ship has been cleared, only the enormous steel framework stretching hundreds of meters remains. This is when the actual dismantling process begins. However, this mass of steel weighing tens of thousands of tons cannot be cut apart arbitrarily. Every cut must be calculated in advance to ensure that the hull remains stable throughout the dismantling process. Next, every enclosed compartment must be tested for gas several times to ensure that no fuel vapor or flammable gas remains. In Alang, Gujarat, India, a gas leak during a ship dismantling operation caused an explosion that killed 5 workers and injured several others when flames erupted while they were cutting the hull. This is why safety inspections are always treated as the highest priority before the first cutting torch is ignited. After careful inspection, the technical team begins cutting the hull from the highest decks. Once the cutting positions have been marked and a final inspection completed, workers ignite oxy-gas flames, reaching temperatures above 3,000 degrees Celsius. Within seconds, the thick steel begins glowing red before separating under a stream of high-pressure oxygen. Each cut slowly opens through the metal, while sparks continuously scatter toward the ground. When the final cut is completed, cranes and load-bearing cable systems gradually lift steel sections weighing from several dozen to more than 100 tons and lower them to the ground. This operation is repeated for many weeks, until the ship that once crossed millions of nautical miles has been reduced to enormous steel sections waiting to be recycled. Once the enormous steel sections have been lowered from the hull, the work is still not finished. For the dismantling teams, this is when the process of extracting the ship's remaining value truly begins. Workers use oxy-gas torches and hydraulic cutting machines to divide the sections into smaller pieces. Bright sparks once again scatter across the dismantling yard as deck plates and structural beams are gradually transformed into standard-sized pieces of steel. A single large cargo ship can yield between 20,000 and 40,000 tons of steel, enough to supply raw material to numerous steel mills. However, not every piece of metal is sent into the same furnace. After grease, old paint, and surface contaminants have been removed, workers separate carbon steel, stainless steel, aluminum, copper, and brass into individual batches. Even a small amount of another metal can alter the composition of an entire furnace load, directly affecting the quality of the finished steel. After sorting, the steel recovered from the ship is sent in different directions. Plates, beams, and bars that remain in good condition can be recut, sold for reuse, or transferred to re-rolling mills without being completely melted. Steel that is deformed, heavily corroded, or unsuitable in size is loaded onto trucks and transported to steel mills. A large ship can generate hundreds of truckloads over a period of several weeks. At the mill, cranes fitted with electromagnets transfer the scrap into charging containers before it is sent into an electric arc furnace or induction furnace. The intense heat causes the steel to glow red and gradually transform into liquid metal. During melting, oxygen and fluxes are added to create slag and trap impurities. Workers continuously take samples and adjust the alloy composition and temperature until the steel meets the required standards. Through multiple furnace loads, the ship's scrap steel is transformed into raw material for new steel products. After refining, the molten steel is transferred to a continuous casting line to create the first steel shapes. The metal is poured into a ladle, an enormous heat-resistant vessel used to transport molten steel between production stages. From there, the steel flows through a tundish, which maintains a stable metal flow and retains any remaining slag before the steel enters the casting mold. Inside the water-cooled copper mold, the outer layer of steel solidifies almost immediately, while the core remains liquid. Rollers continuously pull the emerging strand downward at a controlled speed, allowing the outer shell to become strong enough before leaving the mold. Once the steel has solidified completely, an automatic cutting system divides the continuous strand into sections of standard length. Within minutes, the steel plates that once formed part of the ship have become uniform semi-finished shapes, ready to enter the rolling process. After casting, billets, blooms, or slabs are transferred to the rolling line. They may enter the machines while still hot or be reheated before shaping. Under the pressure of the rolling cylinders, the steel's cross-section is gradually reduced through multiple rolling stands. Billets are usually rolled into bars and small steel sections, blooms form larger sections, while slabs are rolled into steel plates or coils. In modern mills, this process is automatically controlled. In some smaller re-rolling mills, workers still use tongs and guiding bars to rotate and direct the steel between rolling passes. Once the required dimensions have been achieved, the products are cooled under controlled conditions, straightened, cut to length, or coiled before being transferred to quality inspection. After the rolling process has been completed, each steel plate undergoes quality inspection before leaving the factory. At many mills in India, this stage still depends heavily on workers' experience. They measure dimensions using specialized tools, check straightness and thickness, and carefully inspect the entire surface for cracks, warping, or other defects that could affect the steel's strength. Steel plates that fail to meet the requirements are separated and returned to the furnace, while products that meet the standards are marked for identification, bundled, and prepared for transportation. From there, they are loaded onto trucks or trains and distributed to construction sites, mechanical factories, and shipyards. Within a short period, the steel that once belonged to an old ship begins a new life cycle in the structures of the future. After completing inspection and bundling, the steel bars, plates, and coils are lifted by cranes onto trucks, railway wagons, or cargo ships before leaving the steel mill. From there, they are transported to construction sites, engineering facilities, manufacturing plants, and shipyards, where they begin an entirely new stage of use. At their destination, the steel is cut, pressed, bent, welded, and assembled according to the requirements of each project. Bundles of steel bars may become reinforcement for concrete foundations, columns, and floors, while steel plates and structural sections are fabricated into bridge girders, load-bearing columns, railway tracks, shipping containers, and many other industrial structures. Steel batches that meet particularly stringent standards may even return to the maritime industry, contributing to components used in the construction of new ships. By this stage, the material's original identity is almost impossible to recognize. A steel bar inside a modern structure, or a steel plate used in a production line today, may once have formed part of a ship's deck, hull, or cargo hold wall that traveled millions of nautical miles over several decades. The old vessel may have disappeared from the beaches of Alang, but the steel that once formed it continues to be transported, processed, and used in entirely new forms. After decades of crossing the oceans, every steel plate from the ship's hull is cut apart, melted down, and reborn as an entirely new product. Within only a few months, it may appear in a bridge, a skyscraper, an enormous machine, or even another ship continuing its journey across the waves. This is why steel is considered one of the materials that can be recycled almost indefinitely while retaining its original quality. From an old ship to the structures of the future, every ton of steel is beginning a new life cycle. If you enjoy the remarkable journeys behind modern industry, do not forget to subscribe to Factron Process and join us as we explore more impressive manufacturing processes in upcoming videos.